Welcome to the Deep Dive, where we take a mountain of information and distill it into those vital nuggets of knowledge, saving you countless hours. Today we're plunging into one of humanity's most enduring and frankly impressive endeavors, building. From the awe-inspiring feats of ancient civilizations, whose structures still stand as silent witnesses to ingenuity, to the cutting-edge innovations shaping our modern skylines. We often admire the finished product without ever really pausing to consider the sheer complexity, the intricate processes, and the immense challenges that bring these visions to life. It's a journey that spans millennia, embraces diverse materials, and demands some pretty sophisticated management. Okay, let's unpack this. Today, we're taking a deep dive into a fascinating stack of sources that reveal the intricate world of construction. We're looking at it not just as, a physical act, but really as a nexus of history, management, technology, and sheer human ingenuity. Our mission, really, is to extract the most important nuggets of knowledge and insight, offering you a shortcut to understanding the powerful forces that have shaped and, continue to shape how we build the world around us.
What's truly fascinating here is the incredible breadth of our sources. I mean, they span millennia. We're going from unfinished Hellenistic temples right up to the precision of modern building information modeling, or BIM. Throughout our discussion today, we'll explore how approaches to project management have dramatically evolved. It's quite a story. We'll observe the constant dynamic interplay between materials and methods across different eras and uncover the profound impact of design and technology. And alongside these technical aspects, we'll also confront the very human challenges of risk, collaboration, and even the occasional flashes of ego. It's all in there. This whole journey, it kind of leads us to a fundamental question. When we talk about progress in building, what does that truly entail? What does it really mean?
Exactly. And for you, our listener, this deep dive is meticulously designed to provide a thorough, yet hopefully refreshingly accessible understanding. Our goal is to offer you those genuine aha moments without ever feeling overwhelmed by, just tons of information overload. You'll walk away not just well-informed, but maybe with some surprising facts and compelling narratives you won't soon forget, giving you a fresh, insightful perspective on every structure, every bridge, and every home you encounter. Right, so let's begin our grand journey way back, far in the past, to a time of monumental ambition and, sometimes agonizingly protracted realities. Our first significant stop takes us to the Hellenistic Temple of Apollo at Didyma, Miletus. Now, this was no small undertaking. It was a colossal project whose construction, according to our sources, dragged on into the 2nd century BC and beyond without ever being totally completed. Just imagine that scale of effort, centuries of work, and entire civilization's resources poured into it, and still it remained unfinished. It almost defies modern comprehension, doesn't it?
That example from Didyma is incredibly potent, isn't it? It really serves as one of the earliest and most profound illustrations of the inherent complexities, the sheer scale of ambition, and the incredibly long timelines that have always been, and honestly remain, a hallmark of large-scale construction. Even with, relatively less complex technologies compared to today, these projects were pushing the absolute limits of what was achievable, demanding generations of labor and resources. It's staggering. Our sources highlight how Didyma also represents a continuing transformation of this building type, influenced by innovations seen at earlier sites like Marseille. What's particularly significant for architectural historians is its formal aspects and the shift of architectural initiative to Asia Minor during the Hellenistic period. So it shows this fascinating evolution of design principles and construction capabilities across regions. This project, never fully realized, it sets a historical baseline that really forces us to consider the immense challenges these builders faced. And during political shifts, economic downturns, and the sheer logistical nightmare of supplying and coordinating such a vast undertaking over hundreds of years.
That really makes you consider, doesn't it? How even with simpler tools and, less advanced engineering, these ancient projects could stretch on for generations. It sets such a powerful historical baseline for understanding the scale of ambition and the incredible patience required throughout history. It's a testament to human persistence, really, even in the face of what must have seemed like insurmountable odds. From the ambitious, if incomplete, Hellenistic world, let's now transition to Roman ingenuity and their mastery of scale. And the perfect example, of course, is the Pantheon. This structure stands as an enduring testament to the early mastery of concrete and vaulting, a true marvel of engineering. Our sources describe it as circular in plan, covered with hemispherical vaults of concrete, boasting a wall incredible 18 feet thick, and an internal diameter that nearly matches its 147-foot height. It's just monumental for any era, let alone over 2 millennia ago.
Indeed, the Pantheon is a showstopper, and the renowned architectural historian Viollet-le-Duc offered some truly insightful observations on Roman construction. His perspective really helps us appreciate its raw power. He noted that in their forlorn nakedness, Roman ruins exhibit only the essential character of Roman architecture. He was basically arguing that without their original luxurious veneers, the underlying structural genius becomes startlingly clear. It's laid bare. He specifically pointed out the gigantic mechanism of the Roman structure, where the immense vault and the single vast 26-foot diameter opening for light the oculus produces the most lively impression. For Viollet-le-Duc, this directly showcased the genius of the Roman in full strength. It's a powerful statement about raw engineering might and structural innovation. And what's equally insightful, maybe even a bit provocative, is how Viollet-le-Duc contrasted Roman magnificence with Greek taste. He suggested that Agrippa's interior decorations in the Pantheon were probably as an afterthought, sort of illustrating a Roman tendency to add rich, often opulent decoration. But it wasn't of taste, as the Greeks would have defined it. Now, this distinction isn't just about aesthetics. It highlights fundamentally differing philosophies of construction and design. It's really deep. The Romans prioritized scale, engineering might, and creating these vast enclosed spaces, often adding ornamentation almost as a secondary layer.
Yeah.
The Greeks, by contrast, they focused on integrated, harmonious design where proportion and detail were inseparable from the underlying structure. So this gives us a window into the distinct cultural values embedded within their respective built environments.
Right. Okay, so as we move forward in time into the Renaissance, the influence of figures like Leon Battista Alberti on architecture was absolutely profound. He advocated for designs where facades, especially on prominent squares and approaches, would revert to Albertian orthodoxy. Take the Palazzo Rucellai in Florence as a prime example. Here, our sources describe how vertical dividers engage the public space directly. They encourage the passerby to turn around and face the building. It's not just a static structure, it's an active dialogue between the building and its viewer, almost like a theatrical experience.
That's exactly right. Alberti's approach connects directly to a really sophisticated understanding of human perception and urban engagement, deeply rooted in classical ideals. It was a conscious shift from earlier Renaissance styles, like that horizontal layering prevalent in the Medici palace type, which tended to carry the eye along the facade by the perspective, almost guiding you past the building.
Right, it just leads you along.
Yeah. Alberti's use of vertical elements, like pilasters, was designed to stop the viewer, to draw them in, make them confront the building head-on. It's a deliberate, almost psychological approach to architectural design, one that actively shapes how people interact with and experience urban spaces, influencing their movement and attention. Really clever stuff.
Now let's zoom in on a fascinating detail from history that resonates even today. And here's where it gets really interesting for me. Imagine architects centuries ago using seemingly simple geometric shapes to ensure not just structural stability, but also an aesthetic balance that still feels right to our eyes, even now. Our sources introduced the concept of geometric principles in architectural proportion, drawing heavily from Viollet-le-Duc's analysis again. He demonstrated how equilateral triangles could determine pillar height, width, and even the voids, the spaces, within ancient and medieval structures. He cited iconic examples like the Parthenon and the Temple of Concord at Agrigentum as prime examples of Greek application, and even mentioned the Egyptian triangle as a standard of proportions, highlighting a continuity of these ideas across cultures.
Viollet-le-Duc's observations on these geometric rules are profound because they speak to a universal truth in design. They satisfy a requirement of the eye, which demands that the part borne and that which bears it shall not go beyond the angles of an equilateral triangle. Basically, this means structural elements were proportioned in a way that visually conveyed stability and harmony, a sense of rightness that transcends cultural boundaries.
That looks right.
Exactly. And what's even more compelling is that these laws, evidently derived from certain principles of classical antiquity, weren't just confined to ancient Greece and Rome. They persisted right through the Middle Ages. Even when medieval artists and builders were clearly not just copying the form of ancient architecture, they were nonetheless reasoning as the Greeks had reasoned. They were applying these fundamental intuitive principles to entirely new architectural forms like Gothic cathedrals. It speaks to a timeless, almost inherent understanding of structural and visual integrity that guided master builders for millennia.
Okay, so From the enduring principles of antiquity and the Renaissance, let's fast forward quite a bit to a more modern visionary, one whose impact really reshaped residential architecture, Frank Lloyd Wright. His architectural philosophy was deeply rooted in the powerful idea that all architecture, worthy the name, will henceforward more and more be organic. He was a fervent champion of buildings that were not just in their environment, but actively in tune with their environment, embodying truth, beauty, and a response to the environment and human needs. His work aimed for this seamless, almost living integration of the natural world with human habitation.
Yeah, but our sources present a wonderfully nuanced and sometimes, well, challenging view of Wright's genius. They don't pull any punches. They don't shy away from revealing the notorious plague of leaks and rising mildew at falling water. They starkly describe it as a 7-bucket building.
7 buckets, wow.
Right. This isn't just a minor design flaw. It serves as a potent cautionary tale that even an architectural genius like Wright faced significant and sometimes chronic practical challenges. It highlights the inherent tension between a grand artistic vision and the often messy realities of construction and maintenance. The sources also touch on Wright's fatal egotism and the often unchangeable nature of his highly designed buildings. They quip that to live in one of his houses is to be the curator of a Frank Lloyd Wright museum.
Huh. That's brilliant.
Implying that, modifying or adapting his designs for daily life was almost impossible. It illustrates a profound conflict between visionary design and the practicalities of everyday living.
That's a really important distinction, especially with someone like Wright. It makes you wonder, even for a visionary who sought to integrate nature and design so beautifully, those practical challenges highlight the real-world consequences of architectural decisions. Beauty and concept are one thing, but function, durability, and livability are another entirely. And they often come with a far higher cost, maybe not just financial, than initially perceived. Now let's shift to a different kind of visionary. Isambard Kingdom Brunel, an absolute titan of engineering from the Industrial Revolution. We're going to recount the fascinating and at times pretty tragic story of his Great Eastern Ship. This was a truly ambitious project, a marvel of its age, yet our sources describe it as dogged by misfortune, had been checked and was now brought to a grinding halt by human fallibility and folly. Ouch. There were immense financial and contractual issues with his partner Scott Russell, including Russell suspending payments, discharging men, and demanding a fantastic sum of £15,000 a month, which was an astronomical amount for that era.
And Brunel's personal philosophy was famously encapsulated in his belief of no such thing as retreat or the acknowledgement of defeat. He just wouldn't give up. This unwavering determination drove him to proceed with the Great Eastern's construction under his direct supervision, despite these escalating financial and logistical nightmares. The sources meticulously detail the string of accidents, the staggering £130,000 cost to the company that would be multi-millions today.
Unbelievable.
And its eventual sale for a mere £25,000 to bondholders. It looked like a colossal failure, right? However, what makes the story truly compelling is the unexpected twist. These shrewd bondholders then chartered the immense vessel for cable laying across the Atlantic, beginning what became its most useful period and finally realizing a tangible return on its incredible engineering. This journey illustrates a complex blend of grand ambition, technical innovation, severe financial woes, and ultimate repurposing. It underscores that even the most visionary projects are deeply intertwined with human nature, financial constraints, and often an unexpected path to success.
It's incredible how these powerful historical figures connect to this core idea, that large-scale projects have always been a blend of grand vision, technical innovation, and the messy realities of human nature and financial constraints. It's a thread that runs right through time, showing that the challenges of building are as old as civilization itself. It's not just a modern problem. Okay, moving from these grand historical endeavors to the very building blocks themselves, let's revisit concrete. We briefly touched on its use in ancient Roman circular vaults, but its modern properties, as described in our sources, are really a result of centuries of refinement and far more precise scientific understanding. Its composition is critical. Aggregates make up roughly 3/4 of the volume, and these, our sources emphasize, must be strong, clean, resistant to freeze-thaw deterioration, chemically stable, and properly graded for size. Each of those criteria is vital.
The precision involved in modern concrete science is truly remarkable, actually. The importance of a low water-cement ratio for achieving optimal density and strength is paramount. Too much water, and you compromise the material's fundamental integrity.
Right, it weakens it.
Exactly. But to achieve good workability on the job site and to enhance its resistance to freeze-thaw cycles, especially in harsh climates. Specialized admixtures like air entraining or water-reducing agents are now routinely included in the mix. This is a far cry from the empirical Roman methods. Today, most concrete in North America is proportioned at central batch plants, where quality control is rigorous, and it's transit mixed en route, ensuring it arrives at the job site perfectly ready to pour. This sophisticated process stands in stark contrast to smaller jobs where rule-of-thumb volumetric shovel measurements might still be used, or indeed those more rudimentary techniques of ancient builders.
What truly fascinates me about this is the incredible precision of modern concrete mixing compared to, like you said, the rule-of-thumb shovel measurements for small jobs, or even ancient Roman methods. It really highlights a continuous, relentless quest for optimal material performance. We're talking about a science in itself to get that perfect blend, balancing strength, durability, workability for specific applications. Okay, beyond concrete, other foundational materials play absolutely crucial roles, each with its own unique properties and applications. Let's look at masonry and steel. Masonry, in its various forms, includes composite masonry, which for our listeners typically means it involves two separate layers, or withes. You've got a facing withe, which is the exterior finish, and a backup withe, providing structural support, often held together with metal wall ties. And of course, there's the pervasive use of concrete masonry units, or CMUs, basically concrete blocks. Very common.
And then we have steel, which represents a different paradigm entirely, a very different material. It's non-combustible, highly valued for its exceptional tensile strength and ductility. It bends before it breaks, essentially.
That's right.
It's the go-to material for structural steel framing, forming the skeleton of many large buildings. And also in lighter forms like light-gauge joist framing and light-gauge stud-bearing walls. These are often used in residential or smaller commercial buildings where lighter loads and faster construction are desired. What's important to note is that steel framing is most efficient when the girder and beam supports are laid out along a regular grid. This allows for standardized components and streamlined construction, much easier to assemble. Each of these materials brings distinct advantages and structural characteristics to a project, requiring specific expertise for their proper application.
Yeah, these diverse materials offer fundamentally different structural characteristics, and their proper application is absolutely foundational to any building's integrity. The choice of material impacts everything from load-bearing capacity and fire resistance to aesthetic finish and cost. It demonstrates the complex decisions architects and engineers face from the very outset of a project. All right, once the core structure is in place, crafting the building's envelope essentially, its skin of roofing, walls, and insulation becomes paramount. This layer is critical for protection from the elements, ensuring energy efficiency and defining the building's aesthetic. Let's start with roofing materials. Our sources detail options like composition shingles. These come with either an inorganic fiberglass base, offering excellent fire resistance, often designated UL Class A, that's the highest standard from Underwriters Laboratories, or alternatively, there's an organic felt base with moderate fire resistance, typically UL Class C. For more utilitarian structures or those with very low slopes, asphalt roll roofing is commonly employed. Simple, effective.
But it's the hidden details, isn't it, that often determine a roof's true longevity and performance. Features like self-sealing adhesive or locking tabs are absolutely vital for wind resistance, especially on low-slope roofs or in regions prone to high winds.
Yeah, you need that extra hold.
Definitely. Installation details are incredibly precise, often requiring a double starter course and the use of corrosion-resistant nails driven flush with the shingle surface to prevent damage and ensure a tight seal. Furthermore, in colder climates, an ice and water shield is a crucial addition for eaves to prevent severe damage from ice damming, which is a common and really destructive phenomenon. These seemingly small details, meticulously executed, are what truly make a roof protective and durable over decades. It's not just about the shingles themselves.
Yeah, to put this in perspective, even something as seemingly straightforward as a roof involves complex material science and incredibly precise installation to ensure durability, safety, and long-term performance. It's far more than just laying shingles. It's a sophisticated system designed to withstand decades of weather. Now let's turn to walls and insulation. Absolutely critical for thermal performance, structural support, and creating a comfortable interior environment. Our sources explore various options, from rigid insulation with taped or sealed joints, designed to create a continuous thermal barrier and prevent air infiltration, to interior finishes like gypsum board with vapor semi-permeable latex paint, which helps manage moisture within the wall assembly. For low-slope roofs, thermal insulation placement is also varied and strategic. It can be below the deck, nestled between the deck and the membrane, or even placed above the membrane. Each choice impacts thermal efficiency and structural interaction differently.
And we also see different framing approaches that have evolved over time. Balloon framing, for instance, uses full-height studs that run continuously from foundation to roof. While relatively rare today due to fire safety concerns and material efficiency, it was once quite popular. It can still be desirable for projects requiring minimal vertical shrinkage, especially when finishes like brick veneer or stucco are applied directly to the frame.
Interesting.
Yeah, more modern and increasingly popular solutions include structural insulated panels, or SIPs, for both walls and roofs. These panels are engineered to provide a continuous insulated enclosure as well as an air infiltration barrier. They significantly enhance energy efficiency and reduce construction time by integrating insulation and structure right into one component. These choices directly impact a building's energy footprint, its resilience, and the overall comfort of its occupants.
You can clearly see how these material and assembly choices directly relate to energy efficiency and structural integrity, two fundamental concerns in any construction project, old or new. It's all about creating a comfortable, safe, and sustainable interior environment, making our buildings perform better and last longer. Now, all these material and construction choices, from the foundation right up to the roof, are heavily guided and enforced by building codes. These codes are not arbitrary. They are absolutely critical for ensuring occupant safety and public health. It's non-negotiable. A major focus, as our sources highlight, is fire protection, which draws a clear distinction between passive fire protection and active fire suppression systems such as sprinklers. Passive protection is inherent in the structure itself, things like the fire-resistant qualities of materials, the compartmentation of spaces, and the inherent characteristics of different types of construction, categorized as AD, 2, 3, free, and V, which vary significantly in their use of combustible materials.
Right, to elaborate on that, passive fire protection is essentially about containing a fire, slowing its spread, and protecting escape routes. It buys precious time. For example, buildings with large open spaces like atriums must be fully sprinklered throughout the building and often require sophisticated smoke management systems to control smoke movement, ensuring safe egress. A clever concept known as horizontal exits effectively creates separate buildings on each floor level to allow exiting to occur from one protected area into another, providing safe havens within a structure.
Ah, okay, like safe zones.
Exactly. Beyond that, rigorous fire resistance ratings are specified for walls, floors, and opening protectives, which can include specialized fire-rated glazing, all meticulously designed to contain fire and protect occupants and assets. These aren't just rules, they're the accumulated wisdom from countless incidents and tragedies codified into protective measures.
That brings up a fascinating dilemma, though. How do we balance stringent safety requirements, often mandated by codes, with aesthetic considerations and practical construction methods? It must be a constant negotiation between beauty, functionality, and the absolute necessity of keeping people safe. Beyond fire safety, building codes encompass a wide range of other critical requirements designed for public welfare. For instance, our sources mention detailed standards for family or assisted use toilet rooms. These have specific spatial requirements to ensure universal accessibility. This might include a minimum clear space of 60 inches by 56 inches at the water closet and carefully designed door swings to prevent them from impinging on that critical clear space, which is vital for users with mobility devices.
And then there are often overlooked but equally vital standards, such as ventilation requirements for attic spaces. These typically dictate that upper ventilators, located not more than 3 feet below the ridge, are required, along with screens to keep out vermin and birds. Little details, but important.
Right, stops pests getting in. Exactly. These codes, though they might seem incredibly mundane on the surface, are far from arbitrary. They are developed from accumulated experience, scientific understanding, and a public mandate to ensure occupant safety, health, and comfort. These regulations often have a direct and significant impact on design choices, material specifications, and ultimately, the overall cost of a project.
It's clear that these codes aren't arbitrary, but are developed from accumulated experience to ensure occupant safety and health, often with direct impact on design and cost. They're really a testament to continuous learning and adaptation in the built environment, always striving to make our spaces safer and more functional for everyone.
Okay, let's unpack this. Our sources now delve into the very heart of how complex projects are successfully managed. introducing key concepts from the Project Management Body of Knowledge, or PMBOK, which for our listeners is basically a globally recognized standard. It compiles best practices across industries for how projects should be managed. It highlights 5 absolutely vital elements that consistently contribute to project success: plans, outcomes, culture, benefits realization, and risk. Yeah, and each of these plays an integral and interconnected role in the project lifecycle. They're not separate silos. Plans are foundational, right? Providing the necessary information and roadmap for all agreed activities. Outcomes dictate the very direction of the work, defining whether tasks are enabled or blocked to achieve the desired results and meet project objectives. Culture is often underestimated, but crucial. It establishes the level and character of engagement and collaboration within the project team and across the broader organization. How people work together.
So important.
Absolutely. Benefits realization goes beyond immediate deliverables, focusing on identifying and generating the long-term goals and value the project aims to achieve for the stakeholders. What's the real point? And finally, risk involves proactively defining the project's risk thresholds and engaging in continuous risk management activities to anticipate and mitigate potential challenges. Underlying all of this is the profound importance of blending styles, continuing skill growth, and leveraging motivators to effectively influence and grow the project team, ensuring high performance regardless of individual roles.
And what's interesting is that these aren't just buzzwords for project management. They're universal truths for any complex undertaking, not just construction. The human element, strategic foresight, and careful risk assessment are always paramount, whether you're building a skyscraper or launching a new software product. Project management, as our sources emphasize, isn't a rigid, one-size-fits-all endeavor. You can't just apply a template. Instead, they highlight the critical concept of tailoring. This means the deliberate adaptation of approach, governance, and processes to make them more suitable for the given environment and the work at hand. Factors like the specific business environment, the team size, the degree of uncertainty, and the overall complexity of the project all play a significant role in how a project manager customizes their strategy.
Complementing this adaptability, and quite revolutionary in its implications, is the concept of servant leadership. This is a leadership style that focuses on understanding and addressing the needs and development of project team members. It flips the traditional model. Yeah, its ultimate goal is to enable the highest possible project team performance by empowering the team and removing obstacles rather than simply dictating tasks from the top down. Our sources also acknowledge the rise of self-organizing teams, particularly in agile methodologies, where the facilitator role may dynamically shift among team members. This highlights a powerful move towards more fluid, responsive, and people-centric leadership models, even in traditionally hierarchical fields like construction.
What truly captivates me about this is the idea that flexibility and human-centered leadership are becoming increasingly crucial for project success, even in a field often perceived as, rigid and hierarchical. It's a profound recognition that people and context truly matter, and that empowering teams can lead to far greater innovation and efficiency. Within this overarching framework of project management, the construction manager, or CM, plays an absolutely pivotal role. They're kind of the central coordinator and guardian of the project's success. Let's delve into their responsibilities, starting with proactive cost management. Our sources emphasize a proactive, not reactive approach, especially during the crucial design phase. This is where the CM provides timely cost advice to influence decisions before they become fixed and, expensive to change.
Right. This proactive stance requires a consistently maintained, uniform cost estimating framework that evolves from the project's inception right through to construction. It's not static. Estimates vary significantly depending on the project stage. During conceptual stages, a parameter basis by element and project type is used for high-level approximations, ballpark figures, really.
Got it.
As the design progresses, this evolves to a more precise, deterministic estimate with cost data at a unit price level during preliminary and final design phases, much more granular. Crucially, unit costs must meticulously reflect current market pricing, with escalation addressed as a separate and distinct line item, often computed on a monthly rate. This incredible level of detail in financial planning is not just about crunching numbers, it's about making informed strategic decisions that impact the entire project's viability.
This helps you, the listener, understand the immense depth of financial planning and continuous adjustment required long before ground is even broken. It's not a one-time calculation, but a continuous evolving process of estimation, negotiation, and adjustment throughout the entire project lifecycle. Beyond mastering costs, the CM is also heavily involved in time management and meticulous schedule control. It's a huge part of the job. Their core responsibility includes planning and monitoring compliance with the project timeline. And crucially, this process involves on-site contractors in the development and updating of project schedules. It has to be collaborative.
Key concepts here are essential for understanding how complex schedules are managed. Float, for example, is that crucial contingency time built into a schedule. It allows for delays in specific tasks without impacting the overall project end date.
Like buffer time.
Exactly, like buffer time. It's like a small emergency fund in your schedule, a critical tool for resilience. Another critical aspect is the careful procurement of long lead item materials and equipment, those components with extended manufacturing or delivery times. These must be ordered well in advance to prevent cascading delays down the line. The CM also establishes rigorous procedures for evaluating time-related contract claims, emphasizing the absolute importance of timely notice and documentation of project delays. You need the paper trail. It's a constant battle against the clock, demanding meticulous attention to detail and proactive adjustments at every turn.
Yeah, to put this in perspective, keeping a complex project on schedule is a constant, intricate dance between meticulous planning, precise execution, and rapid problem-solving when the inevitable challenges arise. Things always go wrong. It requires vigilance, collaboration, and a deep understanding of every interdependency. Finally, the CM is absolutely crucial for maintaining the stringent quality management that defines a successful project. While the CM monitors contractor compliance with the quality level expected for the project, our sources make it unequivocally clear that the contractor holds the primary responsibility for quality control and ensuring compliance with all specifications and standards. The buck stops with them on quality execution.
Right. Additionally, the CM's responsibilities extend far beyond just monitoring. They are deeply involved in processing contractors' payments in a timely and accurate manner, keeping the money flowing, administering change orders that inevitably arise during construction. Plans always change, and engaging in claims management to resolve disputes efficiently, trying to avoid major conflicts. At project closeout, the CM is tasked with compiling comprehensive documentation of final pay quantities and costs for audit purposes, meticulously gathering all warranty, guarantee, and operation and maintenance manuals, and, if requested by the owner, even overseeing warranty administration after project completion. The job isn't over when the keys are handed over. It's an enormous scope of work, all meticulously designed to ensure the project meets its objectives, remains compliant, and ultimately delivers lasting value.
This truly reinforces that a successful project is a carefully managed ecosystem of many moving parts and responsibilities, extending even far beyond the physical construction phase itself. It's a testament to the sheer organizational effort required. Hashtag 3.3, navigating the legal and ethical landscape. The construction world, with its high stakes and complex relationships, also involves navigating a pretty challenging legal and ethical landscape. Our sources touch upon different contract types, each designed to allocate risk and responsibility in specific ways. These include cost-plus-fee contracts, where the owner reimburses the contractor for all project costs and then pays an additional fee for their services. Open-ended, in a way. And guaranteed maximum price agreements, or GMPs, which set an upper limit for costs, providing the owner with budget certainty while incentivizing the contractor for efficiency.
Yeah, beyond these foundational contract types, partnering is also mentioned as a proactive strategy for collaborative working. It's aimed at fostering cooperation and shared goals among all project stakeholders to minimize disputes before they even start.
Makes sense.
On the legal side, a critical concept is a lien, defined as a claim against property to secure payment of a debt or performance of an obligation. This legal tool underscores the significant financial risks involved for all parties, from material suppliers to subcontractors. It ensures they have a mechanism to secure payment for their work if things go wrong. These various contractual structures fundamentally dictate how risk is allocated, how parties interact, and ultimately the overall success and financial health of a project.
That makes me wonder, how do these different contract structures really influence collaboration and risk sharing on a project? They can significantly alter incentives and behaviors, right? Potentially fostering cooperation or, conversely, creating adversarial relationships depending on how they're set up. Now, when it comes to ethics and the real-world pressures often encountered in construction, our sources shed light on certain practices. For instance, they note front-loading a bill of quantities. This is a practice where a contractor intentionally prices items higher in the early stages of a project, thereby obtaining more money up front, with that margin diminishing on later items of work. While permissible if disclosed, it's definitely a strategy tied to cash flow management.
And choosing between bids can be particularly tricky business, as the sources put it, especially when one bid comes in actually too low.
Yeah, that rings alarm bells.
It can signal several things. It might indicate a genuine error on the part of the bidder, which happens. Or perhaps a creative approach or strategic buying advantage where they've found a way to be exceptionally efficient. Maybe they got a great deal on materials. However, the risk here is significant for both parties. If the low bid is based on a substantial error and the contractor is forced to proceed, they may struggle to complete the work without having to make up the difference out of pocket. This financial pressure can easily escalate, creating tension and disputes. It's a recipe for trouble. This is perfectly encapsulated in the House excerpt from our sources, where Jim feels played in several keys at once by Jonathan. It highlights the delicate balance of trust, self-interest, and the inherent financial stakes in these complex relationships.
This truly underscores the high financial stakes and the intricate ethical landscape within which construction projects operate, sometimes creating immense tension between parties. It's not always just about the lowest price. It's about understanding the motivations, the risks, and the long-term implications of every decision. Okay, let's unpack this. We're moving into the digital age now. For decades, architects and engineers meticulously worked with 2D drawings as their primary output, a traditional approach that required immense skill but was inherently limited in many ways. But our sources describe an epical transition in design practice with the advent of building information modeling, or BIM. And this isn't just a software upgrade, it's a fundamental paradigm change. It fundamentally differs from earlier computer-aided design and drafting, or CAD, which primarily automates aspects of traditional drawing production. BIM, by contrast, is a whole new way of thinking about building data. It's information modeling.
Indeed, BIM's core advantage is its ability to create a digital representation of a building that contains not just geometry, but rich, intelligent data. That's the key difference. It does this by partially automating the detailing of construction-level building models, which profoundly redistributes the allocation of effort, placing more emphasis on conceptual design.
So less drafting, more thinking.
Exactly. Architects and engineers can spend less time on repetitive drafting and more time on high-level problem-solving and creative design. The direct benefits are extensive. It provides easy methods guaranteeing consistency across all drawings and reports. Everything is linked. It allows for automating spatial interference checking, basically, clash detection to prevent costly conflicts before construction even begins. Huge cost saver.
Yeah, finding clashes on site is a nightmare.
Totally. BIM also offers a strong base for interfacing analysis, simulation, and cost applications.
Yeah.
And crucially, it also enhances visualization and communication at all scales and phases of the project, allowing all stakeholders to truly understand the design in 3D.
What's truly captivating about this is how BIM fundamentally changes how architects and engineers work, shifting their focus from merely drafting lines on a screen to higher-level design thinking and data management. It's about creating an intelligent digital twin of the building, not just a set of blueprints anymore. A key component, and really a driving force, behind BIM's power is parametric modeling. This is where BIM captures design intent parametrically, meaning elements are defined by rules and relationships rather than fixed dimensions. This facilitates model creation and editing, and therefore reduces the likelihood of coordination errors, because changing one parameter automatically updates related elements throughout the model. Given the large number of relatively simple parts in a building and typical building rules and relations that govern their assembly, domain-specific tools have naturally emerged to leverage this.
Absolutely. The evolution of BIM has led to specialized design applications developed for more detailed fabrication levels, providing different object families for embedding different types of expertise, tailored tools for specific trades. Our sources cite early, powerful examples for automated steel fabrication like SDS2, Tekla structures, and AceCAD StruCAD. These systems integrate directly with CNC computer numerical control cutting and drilling machines, effectively bridging the gap from digital design to physical manufacturing, dramatically increasing precision and efficiency.
So the design goes straight to the machine.
Pretty much, yeah. Similar sophisticated systems have been developed for precast concrete, metal ductwork, and piping, showcasing how BIM extends its influence from architectural concept all the way to detailed, automated production of building components.
This truly illustrates how this profound move from simple 2D lines to intelligent 3D objects with embedded data transforms the entire building process. It makes it smarter, more integrated, and more directly connected to real-world production, leading to fewer errors and greater efficiency on the job site. It's a huge leap. Now, let's look at some of the most advanced and truly game-changing BIM applications. Here's where it gets really interesting. 4D schedules dynamically link the project CPM schedule activities to 3D objects in the BIM model. Now, for our listeners, a CPM schedule, critical path method, is a project modeling technique. It helps figure out the critical tasks that, if delayed, will delay the whole project. So with 4D BIM, you get a graphically rich and animated representation of the planned construction sequence set against time. You can actually watch the building get built virtually.
The power of 4D for phasing, coordinating, and communicating plan work is immense. It's transformative. It allows project teams to visually understand the construction process over time, identifying potential conflicts or logistical inefficiencies before they manifest on site.
You can see bottlenecks coming.
Exactly. It powerfully supports simulated what-if scenarios, enabling rapid adjustments to the schedule to optimize flow or respond to unforeseen challenges. But it doesn't stop there. We then move to 5D cost management capabilities, where every element in the BIM model can be attributed to what it will actually represent in terms of resources and respective costs. The cost data is embedded. This is incredibly powerful because it enables parametric and dynamic quantity takeoff for bills of materials, meaning the model can automatically generate precise material lists and costs, leading to more accurate estimates and vastly less time spent on manual quantity takeoffs.
So what does this all mean? The core takeaway from this is truly transformative. BIM offers an integrated digital database that can analyze everything from structural integrity to energy consumption, project timelines, and costs. This leads to much more efficient, informed, and collaborative decision-making throughout the entire project lifecycle, minimizing waste and maximizing value. It's truly a digital revolution in construction. Moving beyond the immediate impact of BIM, let's broaden our discussion to the even more encompassing world of ubiquitous computing and how the built environment itself is becoming, as one source puts it, a physically habitable internet, a Hertzian space. That's quite a concept. This refers to a future where digital technologies become increasingly pervasive and networked online, as with the Internet of Things, fundamentally altering our interaction with buildings and cities.
Yeah, this leads us directly to the concept of cyber-physical systems, integrated systems that can sense the world, create data, and respond in real time. Examples are already emerging, such as microelectromechanical systems, or MEMS, tiny sensors found in everything from your smartphone to advanced infrastructure monitoring.
They're everywhere already.
Pretty much. But the sources push this further with the fascinating, almost futuristic idea of smart dust. Microscopic sensors equipped with capacities for inertial sensors, microfluidic actuators, and photovoltaics all network together wirelessly. This could potentially lead to a future where using a computer does not involve looking at a screen, but rather interacting with an environment that is dynamically responsive to us, adapting to our presence and needs. Imagine a wall that senses your body heat and adjusts insulation, or a floor that reports structural stresses autonomously.
Imagine buildings that don't just stand there passively, but actively sense, adapt, and communicate, blurring the lines between the physical and digital. It's a truly transformative vision where our built environment becomes an active, intelligent participant in our lives. Kind of mind-bending. Another incredibly exciting development, and one that really decentralizes this digital power, is the rise of fab labs, short for fabrication laboratories. Our sources describe these as early manifestations of the third digital revolution. What's key about them is their shared, evolving set of core capabilities, allowing not just projects, but crucially, people and projects to be shared among them. It's a network.
This model connects beautifully to Metcalfe's law, which basically states that the value of a network increases exponentially with the number of connected users.
Right, the more people join, the more valuable it gets.
Exactly. In the context of the Fab Lab network, people and projects are mobile, sharing knowledge, designs, and tools across geographically dispersed locations. This allows them to accomplish collectively what they couldn't do individually, fostering a powerful ecosystem of distributed innovation. Now, this isn't anarchic. It's supported by organizational scaffolding. Things like a fab charter that defines common principles, shared inventory of tools, and a standardized curriculum. The collective benefit of having these common standards, even if it means some local optimization is sacrificed, outweighs the cost of being optimal but fragmented. It's a blueprint for decentralized, collaborative manufacturing that could really redefine how we create and innovate.
That raises an important question. How might this model of decentralized, shared digital fabrication empower local communities and fundamentally redefine how we make almost anything, moving manufacturing closer to the end user and fostering global collaboration on a local scale? It's a powerful idea. Okay, while technology rapidly advances, the human equation in construction remains absolutely central. You can't automate everything. Let's confront a fundamental reality that our sources suggest is an inherent part of any creative and technical process: failure. It happens. They cite the example of motorcycle repair, noting that the practitioner of a stochastic art, meaning an art dealing with randomness and uncertainty, experiences failure on a daily basis.
That's such a relatable analogy, isn't it? And our sources really drive home the profound impact of these daily failures. They describe how such setbacks get internalized, often leading to both pessimism and self-reproach. You beat yourself up about it.
Yeah, I can see that.
But it's not all negative. This process is intimately connected to the moral significance of work that grapples with material things. It forces one to get outside his own head and noticing things, to pay meticulous attention to the physical world and how it responds, how it pushes back. This stands in stark contrast to what the sources call the easy fantasy of mastery that permeates modern culture, reminding us that real skill, true mastery, often comes from confronting and diligently learning from mistakes when dealing with tangible objects and unforgiving physical realities. It builds resilience and a deeper understanding of the craft. You learn more from failure sometimes.
That's a powerful reminder to reflect on how a willingness to confront and learn from failure is absolutely crucial in any field, especially one as complex and potentially unforgiving as construction. Mastery isn't just about flawless success, but about how you analyze, adapt, and grow from setbacks. Now let's turn to a truly fascinating and often controversial figure who indelibly shaped the American landscape: Robert Rosas. Our sources describe him as America's greatest road builder, the most influential single architect of the system over which rolled the wheels of America's cars. A huge impact. What's particularly striking and ironic, however, is that he never drove a car in his life. A real paradox for someone who built so much for the automobile age.
The sources offer a compelling, if stark, account of Moses's methods. We're reporting this neutrally, just what the sources say, particularly how to remove people from the expressway's paths, a euphemism for the often brutal displacement of communities that stood in the way of his projects.
Right, a very clinical phrase for uprooting lives.
Indeed. He navigated complex political landscapes, dealing with powerful county machines by offering wondrous gifts of highway or urban renewal proposals. The key was that the financing was all arranged and the plans were already drawn up, making them incredibly difficult to refuse. Presented as a done deal, our sources neutrally report that the jobs, contracts, and premiums would go where he wanted them to go, including opportunities for land speculation by friends of the borough president, who could buy up land cheaply before news of the proposals leaked, then sell it at a huge profit. This is presented as a factual account of the methods employed during his era, highlighting the intricate web of political power, financial incentives, and human factors that were intertwined with vast infrastructure projects. And these had long-lasting implications for urban planning and social equity, which are still debated today.
So, what does this all mean? The implication here is profound. The drive to build, even with immense power and ambition like Moses wielded, always involves a complex web of political, social, and human factors. These decisions, sometimes made behind closed doors, have long-lasting implications for communities and urban landscapes, shaping how millions live and move for generations. It's a heavy responsibility. Shifting our focus now to organizational effectiveness, the insights of management guru Peter Drucker are highly relevant to any large-scale undertaking. He famously stated that each manager needs clearly spelled out objectives. Makes sense. But he didn't stop there. He emphasized that these objectives must contribute to teamwork and team results as paramount, highlighting the interconnectedness of individual and collective performance. It's about the team, not just the individual manager.
Yeah, and this aligns remarkably well with Eliyahu Goldratt's groundbreaking work in The Goal, which really revolutionized thinking about operations management. Goldratt passionately argued for the importance of focusing on the organization as a whole rather than getting lost in local optimums. That's where individual departments optimize their own performance, sometimes at the expense of the larger system. You see it all the time.
Right, sub-optimization.
Exactly. He introduced 3 fundamental measurements for any system. Throughput, which he defines simply as all the money the system generates through sales.
Yeah.
Inventory, all the money currently tied up in the system, like materials or unfinished work. And operational expense, all the money the system spends to turn inventory into throughput. These provide a holistic view of performance, moving beyond traditional accounting metrics to truly understand what drives the system's overall success and profitability.
That makes me wonder, how do these principles, whether from Drucker or Goldratt, apply to orchestrating the vast number of people, processes, and materials involved in a complex construction project. It's about seeing the entire site as a single, integrated system, rather than just a collection of independent trades all doing their own thing. Goldratt further illustrated his concepts with a powerful and highly relatable analogy, a Boy Scout hike. He said, "The idea is to get there together. The team does not arrive in camp until all of us arrive in camp." Simple, but profound. His key insight for improving the hike's speed wasn't to tell the fastest person to run ahead, but to have the slowest person lead, effectively identifying and then exploiting the bottleneck in the system. Put the slowest person first.
Applying this brilliant analogy to a manufacturing plant, Goldratt frequently found that insufficient protection for the existing bottlenecks was the recurring problem. These critical points, the slowest parts, were often left idle or under-resourced, while other parts of the system were working flat out, creating inventory buildup.
Right, the fast parts just make piles in front of the slow part.
Exactly. He then outlined his now famous 5 focusing steps. Identify the system's constraint, decide how to exploit it, subordinate everything else to that decision, elevate the system's constraint, and if a constraint is broken, go back to step 1. Don't stop. This approach often requires breaking established rules or conventional wisdom to ensure that bottlenecks are continuously busy, because idling the slowest part of the process means, by definition, idling the entire system's output. It's a counterintuitive but incredibly effective strategy for dramatically improving overall performance and throughput in any complex project or organization.
Here's where it gets really interesting for me. The idea that by understanding and meticulously managing the slowest, most constrained part of a process, you can dramatically improve the performance of the entire system. It's a powerful and counterintuitive lesson for any large-scale project, from building a skyscraper to organizing a high-performing team. Focus on the constraint. Ultimately, all this discussion about building, materials, management, it all comes back to its fundamental purpose: people and the spaces they inhabit. Jane Jacobs, a keen and really influential observer of cities, deeply explored the challenge of reconciling high densities with great variety in buildings. How do you get density without monotony? She pointed to New York's Greenwich Village as a vibrant example that manages to house people at densities ranging from 125 to above 200 dwelling units per acre without standardization of buildings. It's a living, breathing testament to successful urban diversity.
Jacobs was a fierce critic of anti-city planning and zoning that actively prevented this essential diversity and organic growth. She saw it as destructive. She fundamentally believed that the capriciousness and diversity of the components is one of the most important and most ignored facts about density averages in successful districts. Her work champions the organic, mixed-use, and human-scaled nature of vibrant urban areas over rigid, top-down, standardized planning that often leads to sterile, uninviting spaces. Think of some modernist housing projects.
Yeah, dead zones.
Right. She taught us that the true vitality of a city lies in its intricate ballet of functions, diverse buildings, and countless human interactions, fostering safety, innovation, and just, well, life.
To put this in perspective, even the grandest construction projects must eventually fit into a human context. And how we plan for that have profound, long-lasting effects on daily life, the vitality of our communities, and the very soul of a city. It's about building for life, not just for structure, a really crucial distinction. Connecting Jacobs' powerful ideas to contemporary urban thought, Carlo Ratti, a renowned architect and engineer at MIT, envisions the city of the future. He sees it emerging from collaborative futurecraft at the intersection of the digital and physical worlds, bringing these threads together.
Ratti fundamentally highlights the critical importance of bottom-up actions and citizen empowerment in truly transforming urban spaces. It can't just be top-down tech. He asserts with powerful conviction that there can be no smart city without smart citizens.
Love that quote.
It's great, isn't it? This isn't just a catchy phrase. It means that residents aren't just passive consumers of urban services or infrastructure. They need to be active, informed participants in shaping their environment. It's about leveraging digital tools to foster community engagement, allowing citizens to contribute to and co-create their cities, ultimately integrating digital capabilities with physical reality in ways that genuinely serve human needs and aspirations. Technology in service of people.
As we conclude this section, it's a vital reminder that while we've covered the history, the technical aspects, the management of building, the ultimate purpose remains to create meaningful spaces for people. That responsibility now extends to thoughtfully integrating digital and physical realities in ways that empower, rather than diminish, human experience and community vitality. #tag outro. Wow, what an extraordinary deep dive. We've journeyed from ancient temples, whose construction spanned centuries, grappling with colossal ambition and, inevitable challenges, to the cutting edge of digital fabrication with building information modeling and the futuristic potential of smart dust. Quite a range. We explored the meticulous world of project management, from proactive cost control and time-critical schedules to the nuanced art of quality assurance. And crucially, we grappled with the complex human element of vision, challenge, and collaboration, sometimes fraught with political maneuvers and financial realities, as we saw with Robert Moses, and sometimes uplifted by profound leadership principles like servant leadership or Goldratt's focus on constraints.
Yeah, if we connect this to the bigger picture, you can truly see that the act of building has always been a dynamic, ongoing conversation. A conversation between what's technologically possible, what's culturally desired, and what's practically achievable on the ground. It's a continuous process of learning from both grand successes and, frankly, inevitable failures, constantly pushing the boundaries of what we can create while striving for greater efficiency, uncompromising safety, and genuine livability. The enduring constant in this fascinating story is adaptation and the diligent application of knowledge, whether through ancient geometric principles that resonated through the ages or the complex, interconnected digital ecosystems that are shaping our future right now.
As we wrap up this deep dive, consider this provocative thought. In a world where digital systems are making our built environments smarter, and even the theoretical destination of self-reproducing machines beckons on the horizon, what new responsibilities arise for us, the builders, the designers, and indeed the inhabitants? How do we ensure that our creations serve humanity's deeper needs, fostering connection, sustainability, and well-being, rather than merely catering to our immediate desires or the latest technological capabilities? Something to think about. That's all for this deep dive. Thank you for joining us on this incredible exploration of how we build.